So for diffraction what diffraction is really is the bending of a wave. That is to say, I get to an opening and I bend around it. The wave bends around it. So does it ever strike you as surprising that suppose there is somebody speaking to you, but they are standing behind a wall? You can hear them, right? But you can't see them. So why is it that I can hear around walls but not see around walls? And under what condition could I see around walls? Okay, and the reason is that you can hear around walls, and this is not just if you're in a room, because in a room you could say, I can hear around walls because the sound is going to that back wall and reflecting. But if I had a wall out in the open, right? And if someone spoke, you'd still be able to hear them. Because the sound wave, the size of the wavelength of the sound waves that we use when we speak is comparable to the size of everyday objects, is of the order of meters. And so the wave would bend. The sound wave bounces off the object and bends around it, and that's an example of diffraction. Whereas the wavelength of light is so small that you only see diffraction effects or the bending of the light when I get to openings that are much, much smaller, that are comparable to the wavelength of light. Okay? So it's basically diffraction is the bending of a wave around either an obstacle or a corner. So you can have a single slit diffraction pattern, and I'll show you the demo in a second. You could have a square opening and it will give you a diffraction pattern like this. So you see the characteristic, the center is bright, and then you have bright, dark, bright, dark. For a diffraction pattern, these are not equally spaced. But otherwise, aside from the fact that these are not equally spaced, it looks very much like a double slit interference pattern. This is how a hexagonal opening would look. This is how a circular aperture would look. And so all of these are happening as a result of waves bending through that slit. So let's look at this, the simplest case maybe, which is the single slit. So this is the one we are going to look at. Okay, so as I was saying, this spreading only is significant if the size of the obstacle or the opening is comparable to the wavelength. Why is that? Because if the size of the opening is much greater than the wavelength, then there's not much bending. There's bending at the edges maybe, but most of the light will go through unbent. Whereas the bending is much more significant if these are comparable, or if the opening is less than or equal to the wavelength. So let's think about a single slit. What is happening here? So you have waves reaching the slit. And remember Huygen's principle, which we talked about maybe 2 or 3 classes ago, is that you're thinking of, this is a wave front. Okay, so wave front is how the whole wave is traveling. It's saying every point in this wave front is in step. But you could think of every point in this wave front as being the source of another wave. Okay, so imagine I think of these little wavelets coming from every point on the wave front. Then when they get to the slit, each of those is going to generate waves spreading in a circular pattern. That was true here too, but they all generated waves that were spreading in a circular pattern such that if I took the tangent to the waves at any point, I'd still get a straight line. But now when they have the freedom to spread here, but not here, you understand, I've blocked off some of them. So it's only these ones that are spreading. If all of these could spread, it would continue to be rectangular, but only some can spread. So now there's going to be some spreading, some bending away from the initial direction. So the light rays are not going to travel straight, they're going to travel now at some angle. And as they travel, they interfere, of course, and that interference is going to again produce a variation in intensity or fringes. So once again, we want to locate where the maxima and minima are for this pattern. So to do that, here's what I'm going to do. And so just pay attention to this a little bit because it's very similar to but different from the double slit. Okay, so I'm doing something that very much similar, which is I'm looking at different points that are generating waves and the path length difference between those waves as I get to the screen. This is like the double slit, except all those are coming from the same wave. Okay, all the waves at this slit. So now I have a single slit of some width, and the width of the slit is A. So what I'm going to do first is divide that slit. So remember, I'm trying to look at the path length difference between these waves coming from different points in the slit. And to do path length difference, it's the same thing. It's the geometry that I'm going to use. But what I'm going to do, because I have only a single slit, is to divide it in half. Okay? So if I divide it in half, let me look at the wave that's coming from the top of the slit and from the center of the slit. So this distance between those two waves is half of the slit width. Right? What is the path length difference between these then? Geometry tells me that that path length difference is going to be this side over here. Right? This is the path length difference. And if the hypotenuse is a over 2 and the angle here is theta, this angle is also theta from geometry, then that path length difference is going to be what? A over 2 sine theta. Remember earlier it was d, and d sine theta was the path length difference. Now instead of d, I have half the slit width, a over 2. So the path length difference is going to be a over 2 sine theta. Now, that is the path length difference. Remember, there are waves coming from all of those. So I'm going to have everything in between also for the path length difference. So I've only chosen this wave over here and this wave over here. And these have been shifted by half a wavelength. That means all the waves coming from in between are shifted by less than half a wavelength. So they're going to interfere constructively to some extent, maybe not perfectly. But if the path length difference between these two is exactly half a wavelength, then those two waves will interfere destructively. Likewise, if I took the central wave and a wave coming from this edge, those two waves will also interfere destructively if the path length difference is exactly half a wavelength. In fact, for every wave that is generated at some point here, if any wave is generated here, I can find a corresponding wave at exactly a over 2 away where those two waves will interfere destructively. So for this construction, if these two waves are different by half a wavelength, then every wave originating in the slit has a corresponding wave that is different by half a wavelength. So every wave generated from the slit will be cancelled out by another wave generated by the slit. So this is now the condition for destructive interference. So if I have this relationship, I'm going to get destructive interference, because they are exactly half a wavelength out of step, and that will be true for every point on the slit. So every wave from the upper half of the slit will cancel with a corresponding point on the lower half of the slit. Okay, so that is the condition for destructive interference for the first minimum, for the first dark fringe. Okay, can I do the same for the next dark fringe? So this is for the first dark fringe. Okay, this is destructive interference, the first minimum. Because there is a over 2 sine theta 1 is lambda over 2, I can cancel the 2's on both sides. So this a sine theta is equal to lambda is a condition for destructive interference. Remember I said it's similar to but different from the double slit case. Well, that formula for the double slit case where D was the slit separation, this was the condition for constructive interference there. But now, because everything is coming from the single slit, this is a condition for destructive interference. That's the first minimum. How about the next minimum? I can, now once again, this is a mathematical exercise, but there is a physical aspect to it, which is, suppose I divide the slit into 1/4 segments. And once again, I take the path length difference between these to be half a wavelength. So the wave from here and the wave from here interfere destructively. Then again, it's going to be true for every point on the slit. I can find a corresponding point where the wave will interfere destructively. So this is the condition for the second minimum. Okay, this is going to be true for every point on the slit. So the condition for destructive interference, once again, is for the second minimum is A over 4 sine theta 2 is equal to lambda over 2, or if you like, A sine theta 2 is 2 lambda. So now you see the pattern, right? The next one, I'll divide them into 6 parts. So the condition for the 6 of the slit to interfere destructively will be A over 6 sine theta 3 is 3 lambda over 2. So this is really coming from saying I divide the slit into 6. So A over 6 sine theta 3 is equal to 3 times lambda over 2. And so if I multiply both sides by 2, I get A is equal to lambda over 2. So if I multiply both sides by 6, I get A sine theta 3 is equal to 3 lambda. So the general condition for diffraction minima are going to be A sine theta m is m lambda. There is no m equals 0. Okay? Because this is the condition for destructive interference. All right? And these are not equally spaced. So what you were asking earlier, Shivangi, was that whether the intensity is equal. Because of the diffraction pattern, the intensity will vary. Because in the case of the diffraction pattern, this is not an equal intensity diffraction pattern. In fact, it looks like that. The maximum intensity is directly opposite. And you expect that, right? Directly opposite, everything goes through. Okay, I just want to stop here for a second before I show you the demo and explain to you why this needs wave properties to explain. Okay, so suppose I do the following exercise, and I think I should open up a new, this is a formula that locates minima. Let me just emphasize this. Suppose I had 2 slits and I was sending particles. Imagine I had, like, you know, the thing that dispenses tennis balls when you're trying to practice your tennis strokes. Suppose I have something like that that's sending balls at a screen which has 2 gaps in it. What will I get on the screen opposite? Well, many balls will land directly opposite this slit. Many balls will land directly opposite this slit. And of course, I'm going to get a probability distribution. So I will get something like this. And when I add these up, I will get something like that. So I expect something like a Gaussian curve opposite. If it's a single slit, if I look at, once again, I'm throwing particles through, I should get a probability distribution of them landing directly opposite the slit, and this is slightly shifted, something like that. So getting the central maximum is not the problem. Even with particles, you'll get the second maximum. What you don't get is the fringes. Beyond that central maximum, why do I get dark light, dark light? Why is it, instead of this, looking more like, why do I get something like this? Poorly drawn, but the fact that I get minima in between is what gives me fringes. And that only comes from the wave properties, from the fact that the waves can cancel out at various points. Okay, so I just want you to appreciate this phenomenon for single slit diffraction too. Once again, you can write down a formula by equating the tan and the sine of the angle just like we did for double slits. And you can locate the vertical positions of the maxima on the screen. That will depend on the length between slit and screen. Okay, so in any interference phenomenon, and let me try and switch off these lights and show you this demo. What you're seeing here is the central bright maximum, and then this is the central bright maximum over here, and then you're seeing the subsidiary maxima. And so what your formula is doing is locating the position of the dark fringes there. So this is single slit. How can I change the separation between these? So if the slit width changes, if I change the width of the slit, the size of those maxima change, right? A sine theta is m lambda. So the locations of the minima depend on the width of the slit. If the width of the slit goes down, then angle theta increases and the fringes get wider apart. If the width of the slit goes up, the reverse happens. Okay. Now, if you look at double slit, so coming back to the double slit case, I want you to see this pattern again. And really, what you're seeing over here is both double slit interference and diffraction. So you see the small variations here? That's the double slit interference. Superimposed on that double slit interference is a diffraction pattern. Okay? So you are actually seeing both. You can see it maybe more clearly here. You see that there are actually maxima and minima in between. So if I only had double slit interference, that maxima and minima should continue everywhere. But over and above that, you see that diffraction imposes that I have dark fringes at a certain spot. So there is a modulation of the intensity based on the diffraction.